This will be lecture 6 on fuzzy control. The topic that we will be discussing today is linear controllers using TS fuzzy model. In the last class we discussed how to design controllers for TS fuzzy model when the input matrix is common for all subsystems. Now we will consider the generic TS fuzzy model and how do we design linear controllers for it. So, we will just revise our notion of TS fuzzy model representation of nonlinear systems, then controller design, linear controller design. The approach we will give two controllers for this. So, stabilizing controller design, robust controller approach, we will propose controller 1 and as well as controller 2, two different types of controller. Then simulation results, two link manipulator and ball beam system. Finally, summary.
The TS fuzzy model is expressed in terms of R fuzzy rules, where ith fuzzy rule has the following form. If x1t is f1i and x2t is f2i and so on until end xnt is fni, then x dot t is ai xt plus bi ut. This is my ith fuzzy rule consisting of n states, and each state is a fuzzy variable expressed as a fuzzy variable, and where the fuzzy variable fji is the jth fuzzy set of the ith rule. Then the fuzzy index mu I associated with the ith fuzzy rule is given by this formula. Where mu I j x j is the membership function of the fuzzy set f j I equal to 1 to r. Given an input output pair x t u t, the fuzzy variable around this operating point is constructed as the weighted average of the local models as x dot t equal to summation j equal to 1 to r sigma I a j x t plus b j u t. So, this is my local model, jth local model, and with the jth local model the associated membership function is actually this is actually mu j sigma j. So, sigma j is the normalized fuzzy index associated with the jth local model, and the summation of such local model multiplied with the fuzzy index over j equal to 1 to r gives me the complete fuzzy dynamics in terms of TS fuzzy model. So, a TS fuzzy model approximates a nonlinear system as a cluster of linear system. So, this is my linear system, this is my jth linear system, sigma j is the normalized fuzzy index associated with the jth linear system, and when the cluster of such a linear system, if I R them, if I fuzzy cluster these R number of linear systems, then I get the approximation of a nonlinear system. So, the advantage of fuzzy system is more informative in terms of local dynamics, because I can look at a nonlinear system in terms of linear system. Dynamics is governed by subsystems fired at each operating point. Okay. In this class, we will talk about variable gain controller using Swing-Gill nominal plant. So, this is the first type of controller we will be talking today. In this, we express the fuzzy system as a linear system with a nonlinear disturbance. So, what we will be doing, our fuzzy system which is x dot sigma j equal to 1 to r sigma j a j x plus b j u. This is my T S Fuzzy model, approximation of nonlinear system using T S Fuzzy model. You can easily see that this has a very convenient form, it looks a very convenient form, easy to handle, and this I can write as a x plus b u plus a disturbance term. So, this is my disturbance term. This is the what I am saying here. Express the fuzzy system as a linear system with nonlinear disturbance. Then design a controller to stabilize the linear system in the presence of this disturbance.
Okay. So, that is what I said you, that the original plant was x dot is sigma j a j x b j u, right, j equal to 1 to r. So, this is my original plant. I can always write this plant, you see, as a x t plus b u t. This is the nominal plant, and once I separate from this as a nominal plant, how do I write that? This sigma j a j x. So, in that I have to subtract a x t, which is here. So, sigma j a j minus a x t, okay. I subtract that, and j equal to 1 to r. Similarly, if I subtract b, because b j is there, I subtract b here. How can I do? Because you know that you must know sigma j equal to 1 to r, sigma j a is a, because j equal to 1 to r, sigma j equal to 1. So, you may be worried that I should have only subtracted a outside. No, this is 1. So, hence this is equal to a. So, I can subtract this quantity here. Similarly, about b. So, x dot t is written in this particular form. Sorry, this is my original dynamics. This can be written in this particular form, and this can be finally written as a x t plus b u t plus f x t u t, and this is my disturbance term around this nominal plant. So, where a x t plus b u t is the linear system and f x t u t is a nonlinear disturbance given by, and I represent this nonlinear system in terms of 3 different components. Okay. So, this is simply f x t, b h 1 x t, v h 2 u t. You can easily see that b h t u t is obviously taken into account of this. This one is actually b h 2 u t. You can easily see that this is a nonlinear term, and that is given by b h 2 u t. We can express that. Similarly, this two terms combined represents this one. So, if I say this is the second term, this is my second term. So, this term is represented by this. So, I wish that you understood what we are trying to do. My original plant was given by this particular thing, x dot is sigma j a j x plus b j u. This one I am representing, I am representing this same dynamics as this, there is no difference between this and this, and then I am representing this whole thing as a x t plus b u t. This is the first part, nominal plant, and this f x t as the disturbance, and disturbance has 3 component, whose the first component here I is this one, sigma j b j minus b u t, sigma j equal to 1 to r, and the second component this f x t plus b h 1 x t is this component here. Okay. So, the always in controller design, whenever we say any disturbance, we are not interested in exact representation of this disturbance, rather an upper bound. This is the principle of robust control. We want to know what is the upper bound on this disturbance. Okay. That means, if I am designing my controller for the worst case, naturally the controller also will be stable for the other cases. So, this is the robust control principle, design principle is design the controller for the worst case. Okay. So, that is why what we will do now is that we will represent first of all this disturbance term little more elaborately and define the upper bound. So, let us see the first disturbance term B H 2 u t, the component 1 as I said, which is sigma j b j minus b u t, j equal to 1 to r. We can write this one, this equation as I can because I have to write in terms of b here multiplied sigma j b j bar u t. And what is this b j bar? The b j bar is obviously is such that b j bar is b j minus b. This has to, this identity has to satisfy. So, b j bar is b j minus b. Similarly, f x t plus b h 1 x t is this term, this second term, j equal to 1 to r sigma j a j minus a x t, and then this can be written in terms of 2. Looking at this, you can easily see sigma j a 1 j x t is f x t, and sigma j b a 2 j x t is, I can take out b and I can write this as b h 1 x t. So, here a j minus a has to be written in terms of a 1 j plus b a 2 j. Okay. So, where the a 1 j represents the unmatched disturbance. Unmatched means this disturbance is not you see that this is this disturbance is not magnified by u, means this is not there with the control input. The means matched means unmatched, and this is matched. You see that is b into this, and you see that our normal plant is a x, x dot is a x plus b u. So, anything with b means we can say that this term is like an excitation, because anything multiplied with b is a kind of excitation to the system, and this term is not with b, it is a separate term, unmatched disturbance, and this is matched disturbance, means this is an excitation, external excitation, a disturbance excitation that is exciting the system, because we say b is the control matrix. In that sense, the a 1 j is the unmatched, this one is the unmatched disturbance, and this is the matched disturbance. Okay. Now, we will talk about the control problem. The T S fuzzy model approximates a nonlinear system as a fuzzy cluster of R linear subsystems. Since each subsystem is linear, linear control theory can be applied to design fixed gain controller for each subsystem. Since the desired system output traverses a specific trajectory, system states traverse across different fuzzy zones. It is thus expected that a controller will be characterized by a variable gain instead of a fixed gain, which I have already discussed. So, the control problem is, given a T S fuzzy model representation, design a variable gain state feedback controller u t equal to minus k x t, where k is the variable gain, such that the T S fuzzy model is Lyapunov stable. Here the matrix k represents variable state feedback gain. It is not a constant gain as in case of a linear system. So, now we will be talking about disturbance measure, and since the nominal plant is a linear while disturbance term is nonlinear, one can possibly solve the control problem using the principle of robust control theory. For that, the norm bounds of uncertainties have to be computed first. The norm bound of unmatched state disturbance, which is h 1 x t, which I will show you, which is h 1 x t, is this one. This is matched state disturbance. Matched state disturbance h 1 x t is alpha j. You see h 1 x t, we have represented h 1 x t is this is h 1 x t, you can easily see sigma j a to j x t, sigma j equal to 1 to r. So, that is what we have written here, h 1 x t is sigma j a to j x t norm from j equal to 1 to r norm, overall norm. So, I can represent this particular term using triangular inequality as less than equal to sigma j, and this is the induced norm of a to j is alpha h x j, means alpha h x j represent the maximum singular value of a to j. Okay. This is the maximum singular value of a to j, and the norm of x 2 x t separately. So, this is a triangular inequality, and this is so what we are saying is that we are kind of this disturbance is represented in terms of a measure, disturbance measure, which is less than this quantity. Okay. The norm bound of input disturbance is which is h 2 u t. You see h 2 u t is given here, h 2 u t is this one, and this is sigma j b bar j u t, sigma j b bar j. So, sigma j b bar j u t. So, this was actually sigma j b bar j u t, j equal to 1 to r. So, this can be written using triangular inequality as j equal to 1 to r sigma j and norm of b bar j into u t norm, and we can now write that b bar j norm, the maximum norm. I can put here the maximum norm of induced norm of b bar j is alpha u j, alpha u j is the norm of b bar j. That means, this is the maximum singular value of b bar j. So, this inequality gives a disturbance measure for this quantity. So, where we know already what is alpha u j, we know what is sigma j. Okay. Similarly, the norm bound of unmatched state disturbance, okay, which is f x t. The previous one we have already done matched. So, this is unmatched one f x t, and f x t is sigma j a 1 j x t. So, this whole norm can be written as again less than equal to this a 1 j alpha f is norm of a 1 j, induced second norm a 1 j. Okay, this is alpha f. So, I wish that you have understood now what we have been talking about, the disturbance measure. So, once the disturbance measure I defined, so we will be now telling a theorem which says that if I design a state feedback controller, if I have a state feedback controller for the system, what is the system now? My system is x dot is a x plus b u plus f x plus b h 1 x plus b h 2 u. Okay. So, this is my system, which was original system is simply sigma j a j x plus b j u sigma j equal to 1 to r. So, this is same as this quantity we said, we approximated, and then we found out the measure the upper bound of f x, h 1 x and h 2 u, right. And then we are saying that this system will be stable if this u, control input u, is given by minus sigma j equal to 1 to r sigma j gamma j b transpose p x t. This is my control law, and gamma j satisfies this particular condition where alpha hxj and alpha u and alpha m, alpha f, they are all disturbance measure as we defined just recently, just now, and this can be only valid if these two conditions are satisfied, and that is alpha f is less than equal to lambda mean, that minimum eigenvalue of q, and lambda max is the maximum eigenvalue of p, where A transpose p plus p a equal to minus 2 q. You know that my A is a nominal plant model, and for a nominal plant model A, I can always find out a q for such that I have also p which satisfies A transpose p plus p a equal to minus 2 q. And so, given this p and q, the alpha f which is here, this alpha f, you know that alpha f is the induced norm, you see that alpha f is the induced norm of A 1 j, okay. And this A 1 j is coming from our the term A j minus A. This is can be written as A 1 j plus A 2 j. This is what we have shown earlier. A j minus A is A 1 j plus B A 2 j. So, A j minus A 1 j plus okay. So, this A 1 j is the induced norm is alpha f, means the maximum eigenvalue maximum singular value of A 1 j. So, this is the theorem, and we will just prove this theorem. I again repeat what is this theorem implies. That means, if I propose a control law u t where this gamma j satisfies this condition, then the system will be stable provided alpha f is less than this identity is true as well as this identity is true. Now, consider the Lyapunov candidate V equal to x transpose p x. This is the we are doing the theorem 1 proving, we are trying to prove the theorem 1 now. The time derivative of V is given by V dot is 2 x transpose p x dot, okay. And my x dot, as I have already told you, is A x b u plus f x plus b h 1 x plus b h 2 u, okay. And u is, we have already given u to be, so u is we just defined u is here, this is our u, and if I write down that u is sigma minus j equal to 1 to r sigma j gamma j b transpose p x. So, this is my u. So, before I introduce u inside, let's you see that what I will do is that this is my v dot is 2 x transpose p x dot, and I can write this expression by introducing this x dot inside here. So, if I do that, what I will get 2 x transpose p x dot. So, there is a x. So, what I get is that 2 x transpose p a x. So, this 2 and we know that A transpose p plus p a is minus 2 q. This combined with the knowledge that 2 x transpose p a x, okay. This can be written as X transpose A transpose P plus A P A X. So, you see that A transpose P plus P A equal to minus 2 Q. Then I can write 2 X transpose P A X is X transpose A transpose P plus P A into X, and this quantity is now minus 2 Q. Okay. We have already said that. Given A, we have this in a condition A transpose P plus P A equal to minus 2 Q, if you can write. So, thus writing that the first term 2 X transpose P A X can be written as minus 2 X transpose Q X. Okay. So, this is minus 2 X transpose Q X, the first one. Okay. So, from X dot I took care of A X. Now, let me take care of B U. So, B U is this quantity. So, how do I write it? B U, if I put it here, so 2 X transpose P B U. So, 2 X transpose P B and U has B transpose P X, this one, and the other quantity is that sigma j equal to 1 to R sigma j gamma j. So, because we have already j inside, so instead of j we write k equal to 1 to R sigma k gamma k, right. So, this quantity is given by 2 X transpose P B U, and again we have to multiply f x here, x dot has also another component f x. So, that is 2 X transpose P into f x. Similarly, B H 1 x 2 X transpose P B H 1 x, similarly 2 X transpose P B H 2 U. Okay. So, all that here what we have done, instead of x dot we have replaced this, and we can write the equation like this. Okay. Here further what we can do, we can rewrite this term as kind of a using the properties of matrices, that is X transpose Q X. It can be bounded by two quantities. The lower bound is lambda minimum, that means the minimum eigenvalue of Q X norm square, and the upper bound is the lambda max singular value of eigenvalue of Q norm square, because this Q and P they are symmetric matrices, hence the singular value, maximum singular value is same as maximum eigenvalue, and therefore minus X transpose Q X, if I write this minus, so I can write minus Q X transpose Q X is less than or equal to minus lambda mean Q X norm square. Okay. So, for a symmetric positive definite matrix P, its induced 2 norm is P norm is, we can say induced norm is lambda max P. So, this is my maximum eigenvalue of P, and furthermore if I look at this expression, I am very sorry that this is not capital X, this is small x, bold x, x is a vector, small x. So, X transpose P B X transpose P, you see that this is 2 X transpose P. So, this is not capital X. So, X transpose P B B transpose P X, which is this quantity, this can be written as X transpose P B again X transpose P B transpose, which is B transpose P X. So, in this I can write this as a norm now, X transpose P B norm square. Okay. This is matrix theory. So, taking all the relations into account and using norm bounds on uncertain elements, we get now, earlier we got V dot is this. So, using the norm bound, and using norm bound means this is less than this quantity. So, similarly we can find this is less than this quantity, this then less than its own norm bound, this is the less than its own norm bound, this is less than its own norm bound. So, V dot can be written as a less than some quantity, and that quantity is here. V dot is less than minus 2 lambda min Q X norm square, this is the norm bound of the second term, this is the norm bound of the third term, this is the norm bound of the fourth term, and this is the norm bound of the fifth term. We had 5 terms. Okay. So, by putting that this particular expression, so what we did is that we first derived what is the rate derivative of the Lyapunov function, and then we express that in terms of norm bound using the sign less than equal to, and then this particular quantity can be written as minus 2 x bar transpose q bar x bar, where x bar is this 2 quantity x norm and x transpose p b. This is, you can say, one element, there is another element. This x bar is a vector now, this is the first element, this is the second element, and q bar has 4 element q11, q12, q21, q22, where q11 is given by this quantity, that is minimum eigenvalue of q minus alpha f lambda max of p, the maximum eigenvalue of p. Similarly, q12, q21 is half of this quantity, and q22 is this quantity. And you may be wondering how we got this, but just look at, I will just explain to you in a while, just it's very simple to understand. You can easily see that I can now add all x norm square and this x norm square together. So, that if I add that, you see that this x norm square, if I take common, I get here 2 lambda mean q and 2 alpha x lambda max p. Okay. So, this is so if I combine them, so I can get lambda mean q minus alpha x lambda x, okay, and lambda alpha f lambda max. So, this is my q11. So, you see that if I write this expression as this, and I have taken 2 out, 2 is common here. So, if I take 2 common out, so I get, and I have taken also negative outside. So, this becomes lambda mean q minus alpha f lambda max p, which is this quantity q11 into. So, you see, the point is that you can easily see this quantity, and with the definition x bar is this and this is we can write out q11 x norm square plus q22 norm x transpose p b square, and you can easily see q12 plus q21 x norm and x transpose p b. So, what you saw is that v dot is less than this 5 terms, and I am trying to represent this 5 terms in terms of minus 2 x bar transpose q bar x bar, where if I define x bar as this 2 term, this is the vector of 2 terms, and q bar is to vector to matrix of 2 by 2 matrix, then this x bar transpose q bar x bar is this quantity q11 x bar x norm square, q22 x transpose p b norm square plus q12 q21 x norm into x transpose p b norm. So, you can easily see here that obviously I have to find out this is x bar transpose q bar x bar is this quantity. So, and minus 2 if I take common here, what I get is that easily by comparing the coefficients you will see q11 will be the total coefficients of x1 bar. So, that is lambda mean x minus alpha f lambda max p, which is here q11. q22 is the coefficients of x transpose p b norm square. So, this is one term x transpose p b square and another term is x transpose p b square. So, if I take minus 2 common here, I get here minus 2 common, k equal to 1 to r, k equal to 1 to r, sigma k gamma k, sigma k gamma k, all right. So this is just the first term, and second term is here, where this is sigma j alpha u j j equal to 1 and sigma k gamma k k equal to 1 to r. Okay, so this is q22, and then q12 plus q21 is the coefficients of x bar and x transpose pb. You see that there is only one term, and since we have q12 and q21, the coefficient is simply j equal to 1 sigma j alpha hx j. So this is my coefficient, and I have two terms, so I can easily do that by dividing them equally and making q12 equal to q21. So q12 equal to q21, which is minus half, because here if I take minus 2 common, I am getting minus half here, or minus sign. So minus half sigma j alpha hx j, j equal to 1 to r. So I wish that you understood how we finally wrote v dot in terms of a quadratic function x transpose q bar x bar, and you saw that v dot can be, what is the advantage of this? If I can write v dot as x bar transpose q bar x bar, then if this is q bar is positive definite, if q bar is positive definite, since there is negative sign here, v dot is negative definite, hence the system is stable. Okay. So we can find the positive definiteness of q bar using Sylvester criterion. All principal minors should be positive. So lambda mean q minus alpha lambda x mean p is greater than 0, and determinant of q bar which is this quantity, the determinant of q bar is greater than 0. So this quantity, the first minor first element, which is this is q11 actually. So the q11 it has to be greater than 0. So this quantity gives you, if you go back to theorem 1, this identity, and by assuming by equating this identity, the determinant of q bar has to be greater than 0, then by doing some manipulation q bar, this is the q bar quantity, and then is satisfied if you get this quantity is greater than this. Comparing the coefficient in both sides, we can write gamma k is greater than this for all k. The Weber equation gives constraint on the controller parameter for kth subsystem. As a controller parameter is a positive one, it results in the second constraint in theorem 1, which is gamma k. Okay. So what we actually, so we proved that the theorem is correct, and in the controller 1, what we the salient points are: the linear system considered as nominal plant may not fire at all operating regions, okay, as system is traversing from one point to another point, x1 to xf, okay, x to xf. So then the all the nominal plant, we have selected one of the system matrices A and B of a specific subsystem to be nominal plant. So that may not fire all the time as it moves. Okay. Unmatched disturbance is measured for the entire fuzzy system. Considering the above facts, controller 2 is designed such that the nominal plant changes with the operating region, thus reducing the norm bound on an unmatched disturbance. So what we are trying to say here, in the controller, this one, this desired criteria before we can implement the controller, the alpha f is less than lambda mean q by lambda max p, because this nominal plant, this is a norm bound on the nominal plant. So because the nominal plant, so the distance between the nominal plant and the actual plant where the system has been, the rule is fired, a specific rule is fired corresponding to that is a plant, and this alpha f a kind of a measure, distance measure between the nominal plant and the actual fuzzy, the plant associated with the fuzzy rule that has been fired. So, hence this becomes this condition becomes a little too harsh. To make that relaxed, what we are doing, we are now talking about a second controller that the nominal plant changes with the operating region. Okay. So, as operating zone changes, so whichever rule is fired, from that rule we take the plant. If I have two rules fired, so I consider each of them as the nominal plant. And so, what I am trying to do in the second controller, that let us think two rules are fired, rule I and rule j. So, rule I is x dot is a I x plus b I u, and rule j is x dot is a j x plus b j u. So, what I will do now, so this is I. In this second controller, what we are aiming is that we consider all of them to be nominal plant. Okay. So, this is my nominal plant, as also this is my nominal plant. So, I design a controller u around this plant and controller u around this plant, and then the fuzzy blending of the controller for both the plants is the overall controller gain. Okay. That is the idea for the second controller, which we did not do for the first controller. Considering kth subsystem to be the nominal plant, the T s fuzzy system can be written as this particular one, where x dot t is represented around kth plant, kth the plant associated with the kth rule. Okay. And similarly, the way we did the disturbance term, so fk can be written in terms of 3 disturbance term as we saw for the controller 1. So, all the approaches are same, only thing that's a little difference would be there. And then the controller problem, given a set of R representative dynamics, compute Ek such that each representative dynamics is locally stable, so that fuzzy blending of these individual actions defined as u makes the T s fuzzy model Lyapunov stable. Okay. So, that is what I said here. R representative dynamics means 2 representative dynamics. If 2 rules are fired, okay, if 2 rules are fired, all R rules can be fired actually in principle. So, that is why R representative dynamics. Compute Ek for each subsystem, and then fuzzy blending of u k equal to 1 to R sigma k u k makes the T s fuzzy model Lyapunov stable. This is the idea, and this idea comes from our the first class, that the last class we discussed. Okay. And again the disturbance measure, the way it has to be computed for h 1 k x t, h 2 u t and f k x t, and then the similar manner. And then theorem 2, the controller 2 is suppose that A k is asymptotically stable and P k is positive definite matrix satisfying A k transpose P k plus P k A k is minus 2 q k for some symmetric positive definite matrix q k. Suppose also that alpha f k is less than this quantity and alpha u is less than 1, then the state feedback controller u t is equal to minus gamma k equal to 1 to R sigma k b transpose P k x t, where gamma is greater than this quantity asymptotically stabilizes the uncertain fuzzy model. Okay. So, here you see that this is called k equal to 1 to R sigma k b transpose P k x t, and this is called fuzzy blending of the controller, where we find that gamma has to be greater than this for the system to be stable. And we also relaxed the minimum condition that is required for implementing this controller, where alpha f k is the distance between the kth plant, okay, kth plant and the corresponding jth plant, which is also fired, and normally the distance would be now less. Okay. And the proof is similar to the proof of the theorem 1. So, I will not explain that in this class. You can, this is an exercise for you, that how this theorem can be proved, an exercise. It is similar, just like we proved the theorem 1, theorem 2 can be also proved. So, this is our theorem 2. So, we define two controllers, okay, and the salient point difference between controller 1 and controller 2, an arbitrary subsystem is selected as the nominal linear plant from all sets, from the set of all linear subsystems. The nonlinear disturbance term at each operating point is computed as the deviation of actual dynamics from the selected nominal plant. As the dynamics moves from one operating point to another operating point, the disturbance term also varies accordingly. Whereas in controller 2, each linear subsystem is considered as a nominal plant. The disturbance is modeled for each nominal plant by considering the effects of its neighbor subsystems. The implementation constraint is relaxed in case of controller 2. Okay. So, this is our controller 1, where the structure is minus gamma B transpose P x, where gamma is given by this, and this gamma makes this controller time varying, the gain is time varying. Okay. X is my state. So, minus gamma B transpose P is a time variable quantity, it is not a constant quantity because gamma is varying. Similarly, in controller 2, if you look at here, gamma is a constant quantity, but here sigma I P I makes this again variable quantity. Okay. So, but the design principle between Q1 controller 1 controller 2 are different, whereas the same principle of robust control has been used to design controller 1 and controller 2. Okay. This is our two-link manipulator, okay, and this is our dynamics. We have already been discussing a lot about this. I will not discuss a lot about how you find a two-link manipulator dynamics. So, theta 1 double dot, theta 2 double dot, these are the two joint link angular accelerations, and tau 1 tau 2 minus V 1 V 2, you can write where V 1 is given by this quantity and V 2 is given by this quantity. Okay. And theta 1 and theta 2 are shoulder elbow angle, tau 1 tau 2 are torques applied to shoulder and elbow of the manipulator, and these are the M 1 1, M 1 2 and M 2 1 and M 2 2. So, here we do a little change, little transformation, that is two link planar mechanism needs finite torque at x equal to 0 0 0. So, that means if I have a robot manipulator like this, and if I want to keep this robot manipulator, this is my 0 0 0 position horizontally, and due to gravity it will fall down. So, hence at every joint, this joint and this joint, I have to keep some finite torque I have to apply, so that the manipulator remains stable. But you see that the other case, the vertical position, if I keep the manipulator, so here the torque is required is 0. Okay. So, that is when the no torque requirement, the torque is not required for balancing at vertical upright position. So, if I keep two link one above the other, this is called vertical upright position, okay, which is in the state wise pi by 2 0 0 0. So, then you see that the system is stable, does not require at in equilibrium any control action. So, the control input, if I assume my u is minus kx, so you see that will give 0 input at origin, this will give 0 input at origin, and because it will give 0 input at origin, so if I define this as origin, I require finite torque, it is not possible, but here I require 0 torque, hence I can define this to be origin and I can implement u equal to minus kx. So, to do that, the origin is shifted to vertical upright position by coordinate transformation, phi 1 is equal to pi by 2 minus theta 1. So, theta 1 has been transferred to theta phi 1 by pi by 2, and we make this as the origin. So, now this reversed. So, doing that transformation, what we do, so we have now this this is a transformation, and then the rule base, considering the states x 1 equal to phi 1, x 2 equal to phi 1 dot, there is a transformed theta 1 and transformed theta 1 dot, x 3 is theta 2 and x 4 is theta 2 dot. We did not change that. The system is linearized around the operating point with 0 input. Both x 1 and x 3 are fuzzified into 7 equally spaced regions in range minus pi by 6 to pi by 6. The operating points of the states x 2 and x 4 are always considered as 0. Thus, we have got 49 fuzzy rules and a linear subsystem corresponding to each rule. So, one rule is given as follows. This is just an example. So, we have 49 fuzzy rules, you understand, because what I am trying to do is that we are keeping here, because we have 4 states, but what we are trying to do is that while linearizing x 2 and x 4 we are always making as 0. So, hence x 1 and x 3 they are varying, and x 1 is fuzzy partitioned into 7 as well as x 3 is fuzzy partitioned into 7 equally spaced regions. So, by doing that we have 49 rules. So, if x is around 0 0 0 0, by linearizing using Taylor series expansion you get x dot equal to this quantity a x plus v tau, and similarly I can linearize using this dynamic. I have given this dynamics. So, I can use this dynamics to linearize and then I get this. Okay, you can just do it given the plant model. Once done that, so this is my the linear subsystem around the equilibrium point, around the vertical upright position. So, done that, you see that I have to, in the beginning I have to stabilize the nominal plant. To stabilize the nominal plant, we place the poles at minus 2, minus 3, minus 2, minus 3, and we got these are the state feedbacks. You can use any MATLAB program or Ackermann's formula or any pole placement technique, then you get this again. So, for controller 1, upper norm bound of the mesh state disturbance alpha Hx is found to be 23.3854, and for controller 2, the input matrix for rule 1 is taken as common input matrix. The closed loop poles for all nominal subsystems are selected as minus 2, minus 3, minus 2, minus 3, and the preliminary feedback is given accordingly. The maximum norm bound of mesh state disturbance alpha Hx computed as 8.44536. This is for controller 2, and the constraint on parameter gamma is found to be greater than 27.9, and gamma is selected as 30. So, controllers are proposed for stabilization. To achieve tracking, the overall control input tau is given as tau is minus kx plus u, whereas minus kx is stabilizing control input, and u1 u2 is the tracking controller yet to be designed. So, we can easily design the stabilized fuzzy system dynamics as a form, this particular form, and we have to give now the tracking controller u1 u2 such that it tracks any desired trajectory. So, and the output equation y is my theta 1 position and theta 2 position, okay. And this, using this equation, the y double dot, which is x 2 dot and x 4 dot, if I assume x 1 dot and x 3 dot is my y, then x 2 dot and x 4 dot, because you know that x 2 dot is x 1, sorry, x 2 is x 1 dot and x 4 is x 3 dot. So, using that principle I can write y double dot is a 1 y plus a 2 y dot plus b u, where a 1 is given by the matrices given a 2 1 a 2 2 and a 4 1 a 4 3, a 2 1 a 2 2 a 4 1 a 2 1 a 2 3 a 4 1 a 4 3. Similarly, a 2 is a 2 2 a 2 4 a 4 2 a 4 4, and b is similarly here b 2 1 b 2 2 b 4 1 b 4 2. So, let the desired output vector be y d, and the error vector is defined as E equal to y minus y d, and then I can say u is this my tracking controller, okay. And if I design this tracking controller, I get the closed loop error dynamics as this. So, if I take Kp and Kd as this, then this is a stable dynamics and tracking is possible. So, tooling, manipulator, trajectory tracking, you can easily see that desired trajectory and controller 1 and controller 2, they are very much following, whereas this the other one which is not following is actually proposed by Jack, which is a fixed gain controller for TS fuzzy model, and it is performing very badly, okay. Similarly, here also at a tracking. So, this is a joint 1 and this is joint 2. So, this joint 1 position tracking for both control 1 and control 2 is very good, and here also for both controller 1 and control 2 is very good, but Jack, which is we compared with another algorithm given by Jack, as I said, is not able to do properly. And control input, this is the control input tau 1 and tau 2, which is very smooth, and controller parameters, you see that how the controller is varying at different operating zones theta 1 theta 2. If you see that it is not a flat surface, it is not constant, it is varying. So, variation in gain k 1 1, controller 2, you see that how it is varying over a range. So, performance comparison, controller 1, the RMS error is 0.016 and 0.049, and controller 2 0.013 and 0.036. The performance has been improved. Okay. So, similarly, we can simulate this system for a ball beam system. What is a ball beam system? Ball beam system is, I have a beam and on this I place a ball, and this ball, like it is like this is my beam, and I place a ball here, and the ball will roll over the beam, and the controlling is that I do up and down this beam. So, that means this beam is made up or down, so that the ball always remains in the center point, and this is the dynamics, and for that also we have designed the controller. I will not go in details of this. So, you see that this controller for ball beam system, we could not implement controller 1 as well as Jack controller, we could implement only controller 2, because the relaxation that this controller provided, okay, this is called the relaxation, and this was satisfied for this was not satisfied for ball beam system, whereas it is satisfied for controller 2 for ball beam system. So, none of the subsystems satisfies the condition on norm bound for controller 1, hence it cannot be implemented for this system. So, what I am trying to show, I am trying to show you another system for which the controller 1 cannot be implemented, but controller 2 can be implemented. Controller 2 satisfies the norm bound condition, hence it can be implemented for the system. So, you see that for ball position, the desired and actual very perfect tracking, and this is the tracking error. Okay. So, similarly beam angle, you see that, and controller input. So, summary, in this lecture we have covered the following topics: TS fuzzy model representation of nonlinear systems. TS fuzzy model is represent a linear plant with a nonlinear disturbance term. 2 variable gain controllers have been designed using robust control approach. Simulation results are presented for 2 nonlinear system, showing the comparison, and for references you can see that we have 2 papers here. The first paper is Jack's paper, that is there in IEEE transaction fuzzy system in 1999. The second is our paper, which is in IEEE transaction systems main cybernetics in 2006, okay, which is called variable gain controller for nonlinear system using TS fuzzy model. Thank you very much.